Hi, and welcome to Does Anyone Really Need RAC? I'm Karen Jex. I'm a Senior Solutions Architect at Crunchy Data. I was an Oracle DBA for about 20 years before I started working with Postgres. And for the last few years, I've worked exclusively with Postgres databases, often helping customers to migrate from Oracle to Postgres. And this is a picture of my rescue pups, Shadow and Comet. One of the most common reasons that we hear for not being able to migrate from Oracle to Postgres is the fact that clients absolutely definitively must use RAC. Despite its cost and complexity, Oracle's RAC, or Real Application Clusters, to give it its full title, is still widely used to respond to a variety of performance, high availability, and/or scalability requirements, specifically write scalability. During my time as an Oracle DBA, I loved RAC. When I started working with Postgres, I was quite vocal about the fact that an alternative to RAC was missing. Postgres doesn't have a direct equivalent to RAC, and this seems to deter a lot of people. But does anyone really need it? Over time, and over a number of sometimes beer-fueled debates, I came to the realization that perhaps it wasn't as much of an issue as I first thought. Maybe there are other simpler solutions that could be used instead. A colleague pointed me to Morgan Norgaard's 2003 white paper, "You Probably Don't Need RAC." It seemed like a good starting point for this talk. Norgaard says that if you have a system that needs to be up and running a few seconds after a crash, you probably need RAC. If you cannot buy a big enough system to deliver the CPU power and memory you crave, you probably need RAC. And then with few exceptions, he goes on to say, otherwise you probably don't need RAC. Alternatives will usually be cheaper, easier to manage, and quite sufficient. Norgaard didn't seem to have changed his mind in 2011, saying in an interview, RAC still has all the hallmarks of something people will want to buy. It increases complexity immensely, it's expensive, it requires specialists that are increasingly hard to find, there are always excellent alternatives, and it's pretty much perpetually unstable. Today, I'll talk about what RAC is, what it does, why it's used, and the specific requirements that it fulfills. I'll then look at the various tools and methods that are available that fulfill these same requirements for the vast majority of applications, with the idea of looking at whether or not Norgaard's original statement still holds true. I'm obviously considering the specific case of Postgres, but most of the ideas will also be relevant for other database systems. First of all, what is RAC? The idea here is to give a general overview of what RAC does and why it's used, so I apologize in advance for any oversimplification in my diagrams and explanations. RAC was introduced in Oracle 9i in 2001 as an alternative to the classic single instance database architecture. I'd already been working with Oracle databases for a few years at that point, and I remember it seeming very new and exciting. The RAC architecture allows several instances to be associated with a single database. Applications connect to the database by specifying a service name and the scan IP, a virtual IP address for the entire cluster, rather than an individual host IP address and instance name. Just as an aside, from version 19c, RAC's only available in Enterprise Edition and no longer in Standard Edition. Some terminology that you might hear when RAC's being discussed is the Oracle Automatic Storage Management, or ASM, which enables you to create a clustered pool of storage that can then be used by any combination of non-RAC and RAC databases. Oracle Clusterware, which was introduced in Oracle 10G as the required cluster management infrastructure for Oracle. Prior to that, third-party clusterware was needed. Oracle Clusterware is described by Oracle as a portable cluster management solution that binds multiple servers so they operate as a single system. And the two together form the Oracle Grid Infrastructure. RAC isn't a single product, but rather an architecture. RAC installation and configuration isn't a trivial task. It's an architecture that needs to be carefully designed and built to the specific requirements of a given application. In fact, instructions for setting it up are in a 2-day plus Real Application Clusters guide. The broad outline is to ensure that the server prerequisites are met, create the required operating system users and groups and configure SSH, configure a network between the servers, configure shared storage, install the grid infrastructure, as we saw, Oracle Clusterware and Oracle ASM, configure the clusterware, install the Oracle RAC software, and finally create a database. What are the benefits of RAC? Oracle quotes high availability and scalability as the two main benefits of the RAC architecture. They say Oracle RAC allows customers to run a single Oracle database across multiple servers in order to maximize availability and enable horizontal scalability. They say that user sessions connecting to Oracle RAC can fail over and safely replay changes during outages without any changes to end user applications, hiding the impact of the outages from end users. The database spans multiple hardware systems and yet appears as a single unified database to the application, which all sounds absolutely idyllic. But the claim that no application changes are required should be taken with a pinch of salt. Typically, applications that work well with RAC have been designed specifically to take advantage of the RAC architecture. An additional use case quoted by Oracle is to consolidate database environments. They say reduce infrastructure costs and the complexity of database environments by running more Oracle database instances on fewer servers without compromising isolation requirements. But consolidation of database environments isn't generally considered by most people as a use case for RAC. In fact, virtualization has a much larger role to play than RAC in consolidating multiple databases or applications onto fewer, larger servers. So I'm going to concentrate on high availability and scalability in this discussion. So let's look at high availability in RAC. RAC helps to minimize unplanned downtime. If there's a failure in one instance or server, access to the database is still available via the remaining instances. If correctly configured, connections that would have been serviced by the failed instance will be handled automatically by one of the surviving instances. Clients that are connected at the time of failure are notified. For this, you need fast application notification or FAN to be configured. New connections are redirected to the remaining instances, and the outage is masked from the client and the application by replaying incomplete application requests. So if correctly configured is the main takeaway here. As we saw in the previous list of tasks, RAC installation and configuration isn't a trivial task. It's not a plug and play, one size fits all type system. It's an architecture that needs to be designed and built to your specific requirements. Application services need to be configured to make sure that new connections are redirected to the remaining instances following a failure. Services can be created on all of the nodes, such as service 1 here, or just on certain nodes like service 2 and 3. The services can also be configured with a set of preferred and allowed nodes to increase the options available in case of failure of a node. The application will specify the scan IP and a service name in order to connect to the database rather than specifying a specific instance on a specific host. So a connection to service 1 could be routed to any of the 3 nodes. If node 1 becomes unavailable, nodes 2 and 3 can still service connection requests for service 1. Node 2 still available to service connection requests for service 2, and node 3 for service 3. What RAC doesn't protect us from is disk failure. A failure at the storage level in this example will still cause unplanned downtime and data loss. It's therefore necessary to eliminate the single point of failure at the storage level. And normally that would be achieved through a combination of a robust, tested database backup and restore policy and either physical or logical replica databases. And that's not a secret. Oracle tells users that tight integration with Oracle Active Data Guard, which provides physical replication, and Oracle Golden Gate, which provides logical replication, enables IT teams to maximize Oracle database availability and protection using proven Oracle MAA best practices. RAC can also help to minimize downtime for planned maintenance. It can be used to implement rolling upgrades and patching on a server-by-server basis. In terms of scalability, instances can be added to the cluster without application changes if and when additional resources are needed. From, for example, an initial 2-node cluster, We can add instances to extend to a 4 or 5 or more node cluster. Application connections can then be shared amongst a greater number of instances, increasing the resources available. Resources are distributed amongst the various nodes in the cluster, again, assuming the application and the database have been configured to allow this. The RAC administration and deployment guide says that the combined processing power of the multiple servers can provide greater throughput and Oracle RAC scalability than is available from a single server, although it is possible in certain cases for that not to be the case. So it's really important to benchmark, to test your particular situation to make sure that multiple instances actually gives better performance than one large server. Why we absolutely must use RAC. Many Oracle users are resistant to the idea of letting go of RAC, whether that's with staying with Oracle or moving to a different database such as Postgres. And I understand that. I spent 20 years as an Oracle DBA and I loved RAC. I even loved the complexity of RAC, mainly because I enjoy a challenge. I particularly loved the fact that if we lost an instance or even two, our applications could keep running without interruption. And we needed that reassurance because nodes did actually go down on a fairly regular basis. Perhaps if I hadn't had RAC, I would have made more of an effort to prevent that situation from happening. Until I started working with Postgres, where RAC wasn't available to me, I didn't stop to think how reliant I'd become on it. Of course, we should plan for the situation where instance or server fails and make sure that we have little or no downtime as a result, but we shouldn't expect that to be a normal part of day-to-day operations. When looking at migrating from Oracle RAC to Postgres, and sometimes whilst explaining to us why it isn't possible for a certain application, clients will tell us things like we need 0 downtime or 5 nines availability or 6 nines or 100% write availability, read scalability, write scalability, thousands of transactions per second per node. They don't want a single point of failure. They don't want multiple copies of the data, or they need thousands of concurrent connections. Most of these are genuine requirements, but not necessarily reasons not to consider alternatives to RAC. They generally fall into the high availability and scalability categories. High availability might be stated as 0 downtime, 3, 4, 5 or more nines availability, 100% availability, or no single point of failure. And in this case, that can only refer to instance failure because we've already seen that RAC doesn't cover us for a database failure. And I'm also talking here about real life close to 0 downtime or 100% availability rather than the theoretical and unfortunately impossible mathematical 0. Scalability requirements might include read scalability, so the ability to increase capacity for read-only activity against the database, write scalability, large numbers of transactions per second, or very large numbers of concurrent connections. I've listed a requirement not to have duplication of data under other. We'll cover it in more detail later, but we've already seen that some duplication of data is actually required if we want to be able to prevent data loss in case of database failure. We'll have a look at all of the different requirements in more detail, see where any limitations of Postgres might be, and which methods and tools are available to respond to all of the different requirements. Just like a single standalone Oracle instance or a single standalone instance of any database for that matter, a single standalone Postgres instance won't provide high availability and scalability. There are obviously some limitations. First, if we consider availability, because our application accesses a single database instance that accesses a single set of database files on a single server, whether we have a network failure, an instance failure, for example, we lose one of our main database processes, a disk failure, or a server outage, our application will no longer be able to access the database, and we have unavailability and ultimately unhappy users. In terms of scalability, it's generally recommended to configure Postgres to allow just a small number of concurrent connections. The default value for max connections, the maximum number of concurrent connections that can be established to the database or to the instance, is 100. And conventional wisdom suggests that it shouldn't be set higher than around 300 to 500 in most cases. Because of the Postgres one process per connection model, there are non-negligible OS overheads that are associated with opening a large number of concurrent connections, even if the majority of those connections are mostly idle. It can cause significant performance degradation. In his article, Analyzing the Limits of Connection Scalability in Postgres, Postgres committer Andres Freunde explains in detail the limiting factors, specifically memory usage, snapshot scalability, and connection model. He identifies snapshot scalability as a significant but improvable bottleneck in versions up to 13. The graph on that slide is from his article, where he shows how much the throughput decreases as the number of mostly idle connections increases. In his subsequent post, Improving Postgres Connection Scalability Snapshots, Andres describes the improvements that he contributed to Postgres 14, which was released in 2021, which significantly reduced this identified snapshot scalability bottleneck. And the results of his benchmark tests shown in the graph here suggest that even with up to 10,000 idle connections, throughput now remains stable. Customers often quote that Oracle performs better than Postgres. It's difficult to find benchmark figures that compare like with like, and that should probably be a focus for some testing in another talk or blog post. But anecdotally, the majority of our customers who migrate from Oracle to Postgres see comparable performance, with some operations performing better and others less well in Postgres than in Oracle. Various different benchmarks suggest that a single Postgres node can handle some tens of thousands of transactions per second for certain workloads. This is sufficient for the vast majority of applications, but there are applications out there that need to process hundreds of thousands or even millions of potentially complex transactions per second. This is going to be too much to ask of a single node of either Postgres or any database. So what are the alternatives to RAC that are available to us in Postgres? We'll look at the methods and tools that are available to respond to each of the requirements. And the open source nature of Postgres means that in addition to inbuilt options, there are many third-party tools available, either open source or proprietary. I've not used all of the tools that I talk about in this, but I mention them to discuss the fact that they exist and show that they provide certain functionality. Firstly, high availability. One of the main methods for ensuring continuous availability of any system is to avoid single points of failure. In the case of a database system, this includes both the database itself, the data files, and the database instance, the memory and processes that access the database. In order to eliminate this single point of failure, most database systems provide us with options that allow replication of a primary database to one or more replica or standby databases. Postgres allows us to create both physical and logical replica databases and provides a variety of different options for each. From our primary database, we can have physical replication, an all or nothing copy of the entire database instance that's kept up to date by continually applying changes to the standby database as they occur on the primary. And this uses exact block addresses and byte-by-byte replication. This can be via log shipping, sometimes known as warm standby, whereby WALs continuously archived from the primary and used by the standby for continuous recovery. Or more commonly now, streaming replication, where changes are applied almost immediately on the standby database rather than waiting for a WAL file to be copied over and applied. The replication can be cascaded, so the changes are replicated from one standby to another rather than directly from the primary. The replication can be configured to be synchronous. In this case, the primary will wait for confirmation that the changes have been applied on the standby before committing a transaction. In the case of primary database failure, that means we know that all committed changes have been applied to the standby, so we've got some protection against data loss. The trade-off, of course, is the potential wait for writes if there's network latency or if the standby is unavailable for any reason. Alternatively, the replication can be asynchronous, the default, where the primary doesn't wait for confirmation that changes have been applied on the standby before committing. If the primary server fails, that does mean that some committed transactions might not have been applied on the standby, and we may have data loss. In place of physical replication, we could instead use logical replication, sometimes known as transactional replication. Changes are replicated based on a replication ID, usually a primary key, and a subset of objects can be grouped into a publication. A subscriber database can subscribe to this publication so that just this set of objects are replicated. A publisher database can contain multiple publications, which can be replicated to one or more subscribers. And a database can even be both a publisher and a subscriber, as with database 3 here. Unlike with physical replication, the subscriber database can be accessed in read-write mode. Of course, creating a copy of the database is only one step in creating a high availability solution. In case of failure of the primary database, the baton should be passed to one of the other databases in the cluster, which will become the new primary, and application connections should be rerouted to this new primary database. Ideally, this is going to happen automatically, quickly, and be transparent to the end users. There are many different tools available that allow us to configure high availability in Postgres, both open source and proprietary, and some of those are mentioned here. I'm not going to discuss them all in detail, but I'll briefly describe the way in which a couple of them work, just to give an idea of the functionality they provide. In general, high availability solutions have or should have the following characteristics or functionality. A virtual IP, VIP, or elastic IP that's allocated to the current primary database. Monitoring of the current status of the database in the cluster and of the replication. A way to identify failure of the current primary database and take appropriate action. So promote the appropriate standby database to be the new primary and avoid a split brain scenario by making sure that the failed primary database can't be reintegrated into the cluster. You might have a single tool that performs all of these functionalities, or you might use a collection of components that each performs one or more of the tasks. In addition to minimizing unplanned downtime, a high availability tool or architecture can also be used to perform a manual switchover from one primary to another. This means that we can implement rolling upgrades and patching on a server-by-server basis, i.e. reduce the amount of time that the database is unavailable for planned maintenance. One available component is Patroni. This uses PostgreSQL's native streaming replication together with HA proxy, which is a TCP proxy and load balancer, which allows connections to be routed to the current primary database. The various YAML files provided can then be modified to change the configuration to suit your requirements. So Patroni, according to its documentation, is a template for you to create your own customized high availability solution using Python and, for maximum accessibility, a distributed configuration store, DCS, like Zookeeper, etcd, Consul, or Kubernetes. Crunchy Data's HA architecture of choice is streaming replication, with Patroni used as a failover management utility and etcd used as a distributed configuration store, DCS, containing cluster information such as configuration, health, and current status. And this can be seen in the Crunchy HA PostgreSQL architecture, and seen in this diagram. So we have a Patroni instance per database host. Patroni sends periodic heartbeat requests to etcd that contains the health and status of the Postgres instance. etcd then records the information and sends a response back to Patroni. The Patroni instances use this data to keep track of which database instance is the primary, maintain quorum amongst the available replicas, and keep track of which replica is the most current. It will then determine what to do in order to keep the cluster healthy as a whole. If we have an unhealthy primary database, it will put the database into a fail-safe configuration and trigger an election to promote a new leader. The old primary will be demoted, and if it's available, will then be reintegrated to become a replica. As I mentioned, there are lots of tools available that manage one or more aspects. So one tool that manages all aspects of the high availability is EDB's failover manager, EFM. There's an EFM agent that runs on each of the database nodes and on an additional witness node if needed. The advantage being that this is an all-in-one tool. There's a single tool to install and configure, and a potential disadvantage being that DCS is co-located on the PG nodes rather than being independent. So we might end up with contention for resources between Postgres and the DCS. Another stack that's sometimes implemented is PostgreSQL Automatic Failover, PAF. This is a cluster resource agent that's based on the Corosync and Pacemaker stack. It provides the abstraction that allows Pacemaker to manage Postgres. Pacemaker is used as a cluster resource manager, so it detects and recovers from node failures by making use of the messaging and membership capabilities provided by your cluster infrastructure, in this case, Corosync. This maintains the quorum information. Let's look at some of the options that provide scalability. Some of the methods that can provide scalability are connection pooling to allow a greater number of connections, read-only replicas to provide read scalability, multi-master replication to provide write scalability, load balancing to better manage use of available resources, and sharding to split the database across multiple servers. A connection pooler maintains a pool of connections to the database that can be reused by new connection requests. This can allow a relatively small number of database connections to service a large number of application connections. New application connections can be established and existing ones closed, but the pool of database connections remains constant. Fewer connections are created on the database and less time is taken establishing and closing connections than without a connection pooler. Examples of connection poolers for Postgres are pgpool2, although this does more than just connection pooling, and pgbouncer, which concentrates on doing its one job as a connection pooler well. Read-only replicas, sometimes known as hot standbys, can be used to provide read scalability. We don't want multiple copies of the data is sometimes used as an argument for not wanting to use replication in order to provide read scalability. But as we've seen, we actually need to have at least one additional copy of the database in order to provide high availability and to protect against data loss. RAC users themselves will commonly use either Golden Gate or DataGuard to create a replica database for reporting and/or disaster recovery purposes. Multi-master replication or bidirectional replication can be used to provide write scalability. Multiple copies of the database exist in read-write mode. Changes made to any of the databases will be replicated to the others. Certain applications will be better suited than others to this type of replication. Ideally, applications will be written in such a way that conflicts where two nodes are trying to modify the same data at the same time are avoided as much as possible. Geographically distributed databases or databases that are majority inserts rather than updates might be good candidates for this. A multi-master replication solution will need to handle conflicts if and when they do arise. So one example of a tool that implements multi-master replication is EDB's BDR. A load balancer is a tool that sits between the application and the database and routes client requests to the appropriate database instance in order to distribute the requests across the available resources. pgpool2 is an example of a tool that provides load balancing capabilities for Postgres. Sharding, or horizontal partitioning of the database, is the practice of storing a subset of the data in a number of independent databases. The data could, for example, be split geographically per country or region. This makes sense if you have an application that naturally accesses just a subset of data in the database, for example, regional sales teams accessing data only for their own region. Management of shared data, for example, reference tables, will need to be carefully considered. It might, for example, be necessary to replicate these across all databases. It might also be necessary to access the entire local data set sometimes, for example, to perform reporting. And in this case, we'll need mechanisms in place to allow aggregation of the data in each of the databases. So this could be done, for example, via foreign data wrappers that access each of the databases, or using logical replication to replicate to an aggregated reporting databases. There are a number of tools that provide sharding for PostgreSQL, and probably one of the most well-known would be the Citus extension to Postgres. There's no one ideal, highly available performant architecture. The architecture you design will depend very much on the requirements of the application or applications that will run against the database. You'll need to ask questions such as, what workload does the architecture need to support? Is it for reporting or OLTP? What's the ratio of reads to writes? How complex are the SQL statements? How many transactions per second are expected? Will the database be hosted on premises or in the cloud? How large is the database, or how large is it expected to grow to? What are the business requirements? What level of write availability, read availability, the RPO, the recovery point objective or maximum permitted data loss, the RTO or the maximum permitted length of an outage, the recovery time objective, and what are the specific uptime requirements, how many nines are required. So if we consider workload, we might have, for example, 100 transactions per second or tens of thousands, a handful of concurrent connections or thousands. We might have a database that's a few gigabytes in size, or it might be many terabytes. We might be okay to lose 24 hours of data, or it might not be acceptable to lose any data at all. Perhaps we can afford to wait 4 hours to be up and running after an outage, or we might need to be back up immediately. So we need to make sure that the architecture can deliver the level of performance and availability that we need, but keep it simple where possible. If we have this scenario where we've got a small database, a light workload, and a relaxed RPO and RTO, then a solution involving multi-master replication, load balancing, connection pooling, etc., is going to be unnecessarily complex and expensive. A standalone database with a daily well-tested backup might well be sufficient. If, on the other hand, we've got a large database with a high workload and an RPO and RTO close to zero, a standalone database is clearly no longer going to be enough. We're going to have to put a more complex solution in place. There might also be times when it's actually difficult to migrate from Oracle RAC to Postgres. An application that's currently running well on RAC might have been designed from the ground up with that particular architecture in mind. So it might be difficult, i.e. time-consuming and costly, to make the type of fundamental application changes that would enable it to adapt to certain other architectures. When considering a migration from RAC to another solution, whether it's Postgres, Oracle, or something else entirely, it's essential to analyze the workload and the requirements of the application in detail and make sure that a suitable architecture is designed that's going to meet its needs. It's going to be necessary to weigh the costs and the risks involved in making the required changes against the potential advantages and cost savings involved in moving away from RAC. So to go back to Norgaard's original conclusions and see whether or not they still seem to be true, if you have a system that needs to be up and running a few seconds after a crash, you probably need RAC. If this is the case, you certainly need to design and implement a high availability architecture. But as we've seen in the presentation, there are many different ways that we can design a database system that can be up and running very quickly after a crash. So the solution doesn't necessarily need to involve RAC. If you cannot buy a big enough system to deliver the CPU power and or memory you crave, you probably need RAC. In fact, machines with enough memory and CPU to cope with even the most demanding of workloads are fairly readily available. And even if that wasn't the case, the different replication options available in Postgres mean that servers can be clustered to provide the resources required. Norgaard also said, if you need to cover your behind politically in your organization, you can choose to buy clusters, Oracle, RAC, and what have you, and then you can safely say, we've bought the most expensive equipment known to man. It cannot possibly be our fault if something goes wrong or the system goes down. Okay, fair enough. This argument might still hold true in some organizations. I'll leave the last word to Norgaard, as I don't think I can say it any better. Otherwise, you probably don't need RAC. Alternatives will usually be cheaper, easier to manage, and quite sufficient. Thank you very much for your attention. And there should be time to answer some questions.